Alright guys, a couple people asked for a video, so I'm just going to do a quick video. I'm going to review a little bit of the first part of topic 9 that we talked about last class, and then move into talking about voltaic cells, which is the area of topic 9.2a-ish. Okay, so just a quick review. Oxidation and reduction, which we call redox reactions. We have the oxidation states of two different substances changing. So you have an oxidation reaction and a reduction reaction happening at the same time. So in an oxidation reaction, remember we're losing electrons. A reduction is the gaining of electrons. So both of these are occurring in the redox reaction. And the mnemonic device for remembering this is oil rig. Oxidation is losing, reduction is gaining. Okay. Other people like the Leo says Gur, right? Leo the lion says Gur. In that case, it would be losing electrons is oxidation, gaining electrons is reduction. So either oil rig or Leo Gur, either one is a great mnemonic device for remembering which one is oxidation and which one is reduction. So in these reactions, we have an oxidizing agent, which we call an oxidant, and that is reduced. Okay, so the oxidizing agent is oxidizing something else, therefore it is being reduced. Okay. Conversely, we have the reducing agent, or the reductant, is being oxidized, right? Because it has a component that is oxidized. So in something like this, where we have zinc and hydrogen, you can see that the charges are 0, 1 plus, 0, and 2 plus. So you can see that the zinc is being oxidized, right? It's going from 0 to plus 2. And then we have the hydrogen was being reduced, right, from a charge of 1 plus to a charge of 0. Okay, so the zinc is our reducing agent, and the hydrogen is our oxidizing agent. See if you can do that here just as a practice. If you feel like you get this, you can just skip forward a little bit. But if we have water and aluminum and manganese oxide making aluminum hydroxide and manganese oxide, we see that the charges go something like this. We have 0 to a 3 plus, we have a 7 plus to a 4 plus. So when we're thinking about the oxidation and the reductant, we would say that the MnO4 is our oxidant and that the aluminum is the reductant, right? And you can see that with the charges. Interestingly, powdered aluminum is going to speed up the rate of reaction. Sorry, did I say manganese oxide? Manganese oxide is on the product side, right? Permanganate ion is actually a really strong oxidizer, and it's also quite pretty. How do we balance these? Just as a quick review, remember the key here is conserving mass and conserving charge. So we do what's called half reactions, oxidation by itself, reduction by itself. We practice this in class. So an example of this is like the rusting of metal. So when you have iron rusting, you have a half reaction of solid iron turning into iron ions and spare electrons, and that's oxidation. And the reduction half reaction maybe could be something like oxygen gas is gaining electrons and becoming oxygen ions. Okay, remember the steps in balancing equation? We went over this in class, but I'll do it again. You break up the overall equation into two half reactions. You balance everything for the hydrogens and the oxygens. Then you balance the oxygen by adding water. Then you balance the hydrogens by adding hydrogen ions as needed. And again, this is assuming an acidic solution. There's practice with basic solutions on the website that we went to, right? The Science Geek website. It's a great website. Highly recommend it. Then you add electrons as needed. Now the key, remember the key step, letter E. Don't forget to do this. Multiply each half reaction by the integers in order to cancel out your electrons. If you don't do that, the rest of it gets messed up. Finally, you add the two half reactions and then you simplify. Okay? Now, here's the note about the basic solutions. If you have a basic solution, you just add enough hydroxide to cancel any hydrogen plus ions. And then after that, you simplify. Okay? So that should be straightforward enough. So if you want some practice, you can practice here. We're going to make our half reactions. They look like this. Then we balance. Then we add our water to balance out our oxygen. Then we add our hydrogen ions. And then we add our electrons. Okay, do the same thing down here. We're going to multiply this by 6 in order to balance out the 6 electrons on the other side, which means we have to balance this to 3 and that to 6. And then overall, it looks like we are pretty much fine. So the 6 electrons cancel out. We have 14 hydrogen ions here. And our chlorine ions, and that's going to give us our products. And that should all be right. Okay. Here's another example, but you know what? We're just going to skip forward for the sake of clarity. Whew. This is fun. Okay. This is in a basic solution. Okay, so here in the basic solution, what you would do is after you got to this step, here's what we're going to do. We're going to add 2 hydroxide to this side, 2 hydroxide to that side. Yeah, and so 2 hydrogen ions plus 2 hydroxide ions gives us 2 water, right? So that just changes it just slightly. So we end up with a total of 1 water on the reactant side because the other water cancels out on the product side. And there is your basic solution of a balanced reaction. So all the exact same steps, it's just at the end you add the hydroxide. Okay, voltaic cells. So the big idea here is voltaic cells convert chemical energy to electrical energy, and electrolytic cells convert electrical energy to chemical energy. For the sake of this video, we're only going to focus on the first part of that, which is the voltaic cells. To note, this is also only in spontaneous reactions. So voltaic cells convert chemical energy to electrical energy in a spontaneous reaction. Here's some syllabus statements. Know these. Again, 2 types of electrochemical cells: voltaic, also sometimes called galvanic cells, getting electricity from a spontaneous chemical reaction, and then electrolytic cells drive chemical reactions using energy. So in a voltaic or a galvanic cell, we have electrons being transferred via some sort of external pathway that links the reactants. So a battery is a great example of this. That's what a battery does. Electrodes are another way of doing this. So an electrode is when you have 2 solid metals in a voltaic cell. So each of those are called an electrode. There is an anode, and an anode is going to be where the oxidation occurs, and it's usually written with a negative sign. And then we have the cathode, which is where the reduction occurs, and that's written with a plus sign. The way to remember this, as if we couldn't have more mnemonic devices, I remember anode as anorexic ox, mostly because the idea of an ox being anorexic is ridiculous. And then the other one for cathode is a fat red cat, right? Anorexic ox, the anode is where oxidation occurs. Red cat, reduction occurs at the cathode. Okay. Here is kind of a molecular atomic level look at what's really happening in a voltaic cell. So if you have your 2 electrodes, we have zinc and we have copper in the 2 electrodes. Here you have copper ions floating around and maybe some sulfate ions. Here over here you have some zinc 2+ ions and some sulfate ions. So maybe think about the 2 half reactions that are occurring. What's being oxidized, what's being reduced. It looks something like this when that occurs. It's pretty amazing. So what's really happening here is that the solid zinc is going to be losing electrons to create zinc ions, right? And the copper, see how these are aqueous copper ions, are going to be gaining electrons to be creating solid copper. And that's what's happening here is we started with a solid zinc strip, and the copper from the solution is actually being pulled out of solution and attaching to the zinc electrode. Here's another look at it. So if you look here, what you can see is that the atoms in the zinc strip are losing 2 electrons to the copper ions. When that happens, the zinc atom will actually pull off of the zinc strip, and as you can see, there's like a hole right there. Becomes a zinc ion in the solution, and then the copper ions, these little blue guys, are picking up those electrons that were dropped off by the zinc and becoming a copper atom, which is then attaching to the zinc strip. And you can actually see what's kind of cool about this is you can see the change in the color. This is slightly less blue because remember when we talked about metals a while back that what gives it a color is actually the metal that's in it, and the copper is what gives the copper sulfate this color. And so as the copper comes out of the solution, obviously it's going to lose some of that color. How do we create a voltaic cell? So this is what a voltaic cell kind of looks like. You have a solution of zinc nitrate and copper nitrate, and here you'd put your zinc anode, and then you have your copper cathode, right? And then we have what's called maybe a salt bridge, which has some sort of electrolyte, usually like sodium nitrate, it could be some other ones, potassium nitrate, in some sort of porous gel. In our class, we'll use like a porous cup. Sometimes you can use like a porous barrier. You can even use a piece of paper that's soaked in one of these solutions just to kind of finish the circuit. So in this solution, right, if you think aqueous, we're going to have our zinc, or we're going to have our nitrate, and then over here we have our copper ions and we have our nitrate ions. And the electrons, we have some sort of external voltage, right? Our ions are going to pull electrons this direction and drop the electrons onto the copper cathode. What that's going to do is the zinc atoms will come into solution and become zinc ions, and over here the copper ions that are in the copper nitrate solution will bind to the copper electrode because there's more electrons on here, so we're taking a positive charge plus the electrons. It'll become atoms on the copper cathode. Okay. Why do we have a salt bridge? The salt bridge is used to kind of neutralize the solutions. All right. And what happens, again, I think circuits. So if we have the electrons moving this way, then they need to finish the circuit by continuing to move through here. So the negative charge will continue to move this direction. So the nitrate ions will move that direction, and the sodium ions or potassium ions will move in this direction, right? So think about it just being a full circuit. Yeah? Okay. So the zinc anode will dissolve into the solution. The copper ion plates out onto the copper as the cathode, right? So why do electrons go the way that they do? You have to kind of think that through in terms of that circuit. Here's another way of looking at it. Oxidation on the anode, reduction on the cathode. If you need to pause it and look at it, it shows nicely the movement of cations and the movement of anions. Here we have our voltmeter, which wasn't shown in the last diagram. But again, you can see the zinc, the copper cathode, the zinc anode, the zinc being pulled out into solution, and then the copper being pulled out of solution onto the copper cathode. And then here we have a nice full set of half reactions. There's our half reaction for zinc, half reaction for copper. So the salt bridge is there. We talked about that. So it's some sort of salt solution. The cations move toward the cathode. The anions move toward the anode. And just think about it like a circuit. Here it is again on an electrical scale. The electrons are going to leave the anode, flow through the wire to the cathode. Here's a great example of the porous barrier or salt bridge that would go here. And again, the anode loses mass as the solid metal gets oxidized to form ions in the solution. And as the electrodes leave the anode, the cations that are formed dissolve into the solution. On the opposite side, the electrons reach the cathode. The cations in the cathode are attracted to the now negative cathode. So the cathode gains mass. Here's just another, pretty much the same exact diagram, just on a different level. You can pause it and look at it if you want. You can see that in a salt bridge, this is a great example of how you do that. You'd put it in there and then you put cotton plugs in it and then flip it over. We have these U-shaped tubes. Remember, this is a spontaneous redox reaction, anode oxidation, cathode reduction. Oh, this is really cool because look, there's what a zinc anode would look like and a copper cathode. You see this losing mass and this gaining mass. In class, what we're going to talk about is how to actually write these cell diagram conventions, as well as how to change the voltage. So hopefully you feel okay about this overall, and I look forward to seeing you in class.